Hello everyone, my name is Nikolai Neshov and I'd like to give a talk about our paper Objects Distance Measurement in Augmented Reality for Providing Better User Experience. The authors of this paper are Agata Manova and me. We are both researchers in computer vision area at the Department of Radio Communications and Video Technologies of Technical University of Sofia in Bulgaria. Let me start with a brief introduction of the content of this presentation. At the beginning, I will explain what is the major problem that we are trying to solve and why this problem is a hot topic in the area of computer vision, especially in the virtual and augmented reality. Further, I will explain the proposed algorithm in details regarding the mathematical model behind it. Then I will present the conducted experiments, some picture examples, and the effectiveness of the algorithm with respect to the absolute and relative errors in different environment setup and parameters. Finally, the conclusions will be discussed with some directions of future work. In the recent years, augmented and virtual reality technologies are being used in a wide range of applications and have a big impact over the user experience. Many head-mounted displays provide immersive environment by embedding virtual content in a real-world scenario. So one of the main challenges is intuitive interactions with virtual content. Hence, providing interaction in augmented reality is related to correct interpretation of depth and distance from head-mounted display to the real objects. There is a large number of augmented reality applications where measuring the distances to the real object is essential. The list includes, but is not limited to, for example, prototyping large structures, helping facility managers by providing building information at place, improving the functional vision of people with near complete vision loss, augmented reality assisted interoperative distance systems, etc., etc. Yet many researchers confirm that the distance underestimation is not completely understood. Inaccuracy in distance measurements leads to unacceptable errors degrading the interaction performance. For example, differences in distance perception for real and virtual objects may affect pointing accuracy. So in our work we are trying to solve this problem, and the main goal in our paper is to propose a platform and an algorithm for augmented reality applications that provides the user with information regarding distances to some of the observed objects in the scene. In this slide is shown the main architectures of the proposed system. The two cameras simultaneously providing video frames are attached to the head-mounted display and are shifted at a known distance r with respect to the scene. The first camera delivers video directly to the head-mounted display. Hence, the user can view the real scene. Both video streams are passed to the first block, scene semantic segmentation, where we apply deep learning algorithm based on the DeepLab version 3 model in order to distinguish different objects and find their respective edges. In the next step, object projection size computation, a bounding box for each object is constructed and the height of the bounding box is considered as the size of this object. The sizes for all objects act as input in the next step, distance computation. The computed distance along with the object label is embedded over the image and is shown to the user via the head-mounted display. In order to calculate the distance in real units, we utilize the traditional pinhole camera model. Let's assume that camera 1 is our reference camera. That is, we want to calculate the distance d between camera 1 and object on the scene. As already mentioned, we assume that the two cameras are shifted between each other at a distance r. Moreover, we also assume that the distance t between the two cameras in parallel direction with respect to the scene plane is much smaller than the distance from camera 2, camera 1 respectively, and the object. Given an object with height h, the projection of this object to camera 1, that is h1, will be smaller than the projection of the same object to camera 2, that is h2. If the aforementioned assumptions are accomplished, we can build our mathematical formulation for calculating d with the help of the model depicted in the next slide. The relations between the height of the object and the distances to the first and second camera can be described by equation 1 and 2 respectively, where f is the focal length of the first and second camera, which obviously must be the same. From these two equations, we deduce equation 3 for the desired distance d. It can be seen that this is a very effective and simple way by which we can estimate the distance to the object based on the pinhole camera model applied for both of the cameras. Now I'm going to show you the conducted experiments for the proposed algorithm. We investigated the absolute and relative errors in distance measurement using an object, a bottle, as it can be seen on this slide. In figure A and B are presented the images captured by camera 1 and camera 2 respectively, and in figure C and D are shown the corresponding segmentation masks. As expected, you can see that the object on the left mask looks smaller than the object on the right mask. In our experimental setup, the object was placed at different distances with respect to the cameras. Moreover, we assessed the error against different values of distances between the cameras. So you can see in this slide that a total of 30 experiments were conducted, ranging the distances to the object from 94 to 191 centimeters, and the distances between the cameras from 5 to 25 centimeters. In this slide we can see the absolute and relative errors in figure A and figure B respectively. The smallest error is observed when the object is near the cameras. As the distance increases, the average error increases. This behavior is expected because as the object moves away, its projections become smaller. Since the resolution in measured size is only 1 pixel, as the object gets smaller, the step between two possible calculated distances is getting higher. That leads to increase of the error. Therefore, the error also depends on the correct detection of the bounding box of the object. From these results, a conclusion can be made that the smallest relative error is below 1% and the largest one is below 17%. However, the average relative error is around 4%. Among all experiments performed, the error exceeds 5% only for 6 of all 30 cases. In the top part of this slide is depicted an example image of 3 objects shown to the user via the head-mounted display. The algorithm embeds the relative information, type of each object as detected by the semantic segmentation algorithm, the bounding boxes and the calculated distance. The real distance to each object is: car is at 100 centimeters, bottle at 150 centimeters and monitor at 200 centimeters. It can be seen that the maximum error in this example is around 3 centimeters for the object at 200 centimeters. On the bottom part of this slide are shown the segmentation masks for the images captured by the first and the second camera of the 3 objects along with the estimated bounding boxes. As a conclusion on this work, we propose an algorithm for distance to object measurement using 2 cameras attached to an Oculus Rift head-mounted display and placed at a known distance with respect to the scene. The algorithm presents to the user the following information: bounding box and label, type of recognized object as well as the distance to it. From the experimental results, it can be concluded that the relative error does not exceed 5%. As a future direction, we plan to investigate how to improve the deep learning algorithm for semantic segmentation for higher resolution images. The intention is to tune up the algorithm to produce optimal accuracy for large distant objects while keeping the processing in real time. Thank you for your attention, and I'll be available for discussing any questions, remarks, and suggestions on this work.